The soul may or may not feature as a necessary condition in man's thoughts about the universe, but the universe has been for man a symbol of the eternal, the constant. This astounding conglomeration of the sun, the moon, the planets, the stars, and the faraway constellations has forever tempted man's imagination. From prehistory to the Bronze Age, man imagined the universe to be lunar-centric, which later became solar-centric and later went beyond the solar system to the Milky Way. Mathematics, playing a very important role in the development of modern cosmology, has thrown up hitherto undiscovered areas in man's cosmic quest. In the 15th, 16th, and 17th centuries, natural sciences broke away from the stranglehold of religion. Some of the leading scientific minds who made it possible were the Polish astronomer Nicholas Copernicus, 1473 to 1543. The Danish astronomer Tycho Brahe, 1546 to 1601. The Italian astronomer Giordano Bruno, 1548 to 1600. The Italian astronomer Galileo Galilei, 1564 to 1642. The German mathematician, physicist, and astronomer Johann Kepler, 1571 to 1630, and the English mathematician and physicist Isaac Newton, 1642 to 1727. At the end of 3 decades of intense observation, experimentation, and calculation, Copernicus was able to restructure several common assumptions in astronomy. His intricate calculations and drawings that emerged out of his experiments proposed a sun-centric universe instead of Ptolemy's Earth-centric one. His path-breaking finding that the sun forms the core of the solar system, that the Earth revolves around the sun and not vice versa, various planets follow a distinctive path around the sun, and that the orbits of the heavenly bodies encircling the sun are circular. In the era before the invention of the telescope, astronomy reached new heights with Brahe. Bruno made connections between the mathematical findings of Copernicus to religion and philosophy, and as a result incurred the wrath of the church and was burnt at the stake. Bruno made some spectacular statements about the universe. He said that the universe is infinite, that it existed before creation and has been present since eternity. Nothing can be identified as the core of this universe, and that the stars are actually suns. However, there is some dispute about the scientific and philosophical content of these statements. Galileo propounded the primacy of the experimental method in science. Through intense observation through the telescope, he described in detail the phases of Venus, sunspots, mountains on the moon, and the moons of the Jupiter. He also proved that just like the other planets and the moons, the Earth too moves around the Sun. A frown made Galileo write that the Earth does not move, but the Earth moves and will move despite all the frowns. Like Galileo, Descartes also believed that the Earth revolves round the Sun, but he took fair warning from Galileo's persecution by the Church, and he kept his findings secret. Johann Kepler got an opportunity to work at Brahe's laboratory in Prague. Using Brahe's data, he put forward his 3 laws of planetary motion. A. Each planet travels an elliptical orbit with the Sun at one focus. B. For a given planet radius, the vector to the Sun sweeps equal areas in equal times. C. For any 2 planets, the squares of the periods are proportional to the cubes of the distances from the Sun. Over thousands of years, scientists and philosophers, from Thales to Kepler, have been untiring in the quest for the locus of the solar system. The quest ends with Johann Kepler. A new revolution in science was initiated with Newton's discovery. He expanded the vista of mechanics to cosmic mechanics. Drawing on Galileo's laws, he demonstrated a relation between the mass of falling objects and the motion of planets. Applying the law of dynamics to cosmic bodies, he proved that gravity is an inherent quality in all bodies, and the laws of gravitation are equally applicable to the cosmic universe. Perhaps no other scientist has contributed so extensively to all the 3 aspects of astronomy: theory, application, and discovery through observation. Isaac Newton proved conclusively that not only was Kepler's method most accurate, that was in fact the only method. While talking about the universe, Newton made a distinction between 2 kinds of mass, namely internal or materialistic mass and gravitational mass. He knew that the value of the 2 kinds of mass would be the same for the same body.
This is the Sun, mostly hydrogen and helium. Its surface temperature is nearly 10,000 degrees Fahrenheit. For energy, our Sun converts 700 million tons of hydrogen into 695 million tons of helium every second. The Sun is part of a solar system formed
Just as Newton explained the why to Kepler's theory, Einstein proved the same to Newton's findings in his theory of relativity. Einstein brought about a revolutionary change in the perceived notions of space, time, and motion. In the process, He solved several cosmic riddles and completely redefined the perception of gravity. The path of a falling object does not exactly resemble the elliptical path of planets around the Sun or the moons around the planets. If the similarity had been apparent, then the ancient Greeks would have discovered it a long time ago. Thousands of years later, Newton discovered in the 17th century that the gravitation that controls the moon also controls a falling apple from a tree. Newton's and Einstein's thoughts were quite similar in some aspects, hence the similarities in the theories and even the descriptions that they offer. But there was a subtle difference between the theories of Einstein and those of his predecessors in the field. Newton's findings showed that the gravitational force of the planets could fully explain the nature of the movement. Einstein, however, dispensed with gravitation. Instead, he reconciled Maxwell's equations for electricity and magnetism with the laws of mechanics by introducing major changes to mechanics close to the speed of light. This later became known as Einstein's special theory of relativity.
Successful radioactive poisoning of the atmosphere and hence
in his paper on mass-energy equivalence, Einstein produced E equal to mc square from his special relativity equations. General relativity is a theory of gravitation. According to general relativity, the observed gravitational attraction between masses results from the warping of space and time by those masses. General relativity has developed into an essential tool in modern astrophysics. The general theory of relativity is based on gravity. This theory describes the world as a four-dimensional space-time continuum. The inextricability of this four-dimensional space-time continuum is disturbed due to the presence of matter. The space becomes a curved space. The condition of the curved space is commonly known to us as gravity.